Hi, in this series of videos we're going to learn about confidence intervals. On this specific PowerPoint we're going to have a brief review of sampling, a brief review of the central limit theorem that you should remember from your previous stats class. We're going to learn how to do how confidence intervals work, why we use confidence intervals, how we calculate confidence intervals using Excel, and how we interpret confidence intervals in Excel. Now, on this specific lecture, we will concentrate on these four points. So, just as a reminder of your previous videos on sampling, we know that a sample is a subset of the population. It's a collection of elements from that population. I have it here graphically represented. I have the population of all CHHS students, and we can take a sample of those. Right? We will rarely be able to observe an entire population, and frankly we don't need to. We can make inferences from a sample, right, about a population. So sampling has a problem though, right? That the sample itself may be different from the population. It might not be exactly like the population in its composition, but if it was collected in an unbiased way, it is still representative. Right? Again, if you don't remember this, you should go back and watch the sampling videos. Now, it is very unlikely that a sample will look exactly like the population in its composition, and this is because of sampling error. Right? It is not because of bias. It's not bias. It can still be a representative sample if it's a probabilistic sample, but it will not look exactly like the population, and that is because of sampling error. We assume that every sample has a degree of sampling error. Let me give you an example. Let's suppose we have a population of CHHS students, and we collect a sample. It is a random sample of 10 students. Now, we know here, if we were able to see the population, we would know that 65% of the population of all CHHS students are orange, have orange faces. Right? All students are happy, smiley, and 65% of them are orange. Now, let's suppose we take a random sample and then calculate the proportion of orange students in that sample. Right? We have 1, 2, 3, 4 orange students out of 10. Right? That gives me a proportion of 0.4, right? Or 40% of the students in my sample are orange. But the population proportion is 65, right? So my sample doesn't have the same composition or the same proportion of orange students as the population does. Now, my sample is still representative, right? Because it was selected randomly. It's an unbiased sample, but it's different. And that difference is explained by sampling error. So sampling error is what explains the differences between an unbiased sample and a population. Now, if the samples that we're going to take will always vary, right, will always be different than the population itself because of sampling error, then can we talk about a population just with sample data? Right? How can we do it if they're going to be different all the time? And by the way, we assume that they're different all the time. How do we do it? And that is the magic of statistics, right? Statistics allows you to do that. Now, how? And some of you may remember why and how statistics is able to help you from your previous class. So this is a reminder of that. Now, statistical theory tells us that in general, when we take random samples from a population, let's say a population, regardless of how it is distributed, has a mean mu. Right? Let's suppose it has a mean mu. And we take many samples from that population. Right? Now the means of those samples, right, will follow a normal distribution with mean mu. Right? So if we take hundreds and hundreds of samples and calculate the means and standard deviations for those samples, all those samples that we calculate, all those sample means, will follow themselves a normal distribution with mean mu. And this is regardless of how the original population was distributed. Right? That result is the central limit theorem. Right? Now, the central limit theorem, you should have seen this in your Intro to Stats class. It is, in my opinion, the most important result in statistical theory. The most important result in statistical theory. And it's basically this, that when we take random samples from a population of mean mu, regardless of how it is distributed, the means of those samples will follow a normal distribution with mean mu. Now, we use this to make inferences. Right? Now, let me explain to you that before we go there, before how I explain how confidence intervals work. Let's see what the central limit looks like in this graph. So suppose that we have a population that has a mean mu. Right? And then we take many samples of size n, right, and calculate the sample mean of each of those samples. Right? Each of those has x, right? And their standard deviations, right? And then we plotted all those means. So all the means that we get from these samples, we plot them. We would get, according to the central limit theorem, something that looks like this. So let's say we have we take an x, and then another one, another one, thousands of them. The majority of them, of those means, right, will be very close to the population mean mu. The majority of those sample means will fall very closely to the population mean mu. Some of them will fall a little far away from it, and some of them will fall very far away from it. But now, notice this. Not many of them, and this is a density curve, not many of them will follow very far away. Right? This is what a normal distribution looks like. Not many of them will fall way above the population mean. And not many sample means are going to follow way below the population mean. Now we can use this to calculate confidence intervals. Now, how do confidence intervals work? So, for every sample that we get x, right, we will calculate a confidence interval around it. Right? And we know from the properties of the normal distribution, right, that approximately 95% of all the observations in a normal distribution will fall about 2 standard deviations away from the mean. Right? So when we construct confidence intervals, we get the sample result and we create a confidence interval that is about 2 standard deviations away from that mean when we want to be 95% sure. Right. And then we will, and because of the central limit theorem, we will know that 95% of the time, or 99% of the time, however we construct this interval, we will know that the population parameter will fall in that confidence interval 95% of the time or 99% of the time, depending on how we construct this. right? We won't know exactly where the population parameter lies, right? Because we will never be able to observe the population. But statistical theory allows us to say that, 95% of the time or 99% of the time the population parameter will fall in this. Let me show you that graphically. So we will never observe the population parameter, like I said. But we will take a sample, right? So suppose we get a sample and calculate the mean of that sample, that's x. And we calculate a confidence interval. In this case, this is a 95% confidence interval. Now, this is how all the samples from that population are distributed, right? So how all the means for those samples are distributed with mean mu, which is equal to the population mu. Now we got this sample here, sample mean x. It is above the population mean, it's higher than the population mean, right? But the population mean falls within that 95% confidence interval, right? Now suppose we get another sample and calculate the mean. Now, this sample mean is below that population mean, but the population mean falls within that confidence interval. It is in that confidence interval that we're going to calculate, that you're going to learn how to calculate. Now, I want you to see this. How about if we calculate and take another sample and we get a mean that is extremely low, way below the population mean, way below the population mean. Now, our confidence interval will not have the population parameter in it, right? It's out. This sample mean was so low that it's out of that even it's not capturing the population parameter even in the 95% confidence interval. Now, that can happen, but here's the trick. We know that can happen, but that would happen only 5% of the time. That will happen only in 5% of the samples that we take. That they will be out of the confidence interval. In this case, we know that samples that are so low that the population parameter is not in the confidence interval, right, are going to occur only 2.5% of the time. Only in 2.5% of all the samples that we take, we're going to have a sample mean so low that the population mean is not in the confidence interval. And similarly, only in 2.5% of all the samples, the sample mean is going to be, it's going to be so high that the population parameter is not going to fall in the confidence interval. So, in summary, representative samples are not likely to look exactly like the population because of sampling error. Right? So, sampling error is something that we expect from any sample. And we use statistics to deal with it. That's why we use statistics. That's the reason to be for statistics, to deal with sampling error. Confidence intervals are a way to deal with sampling error so that we can make accurate inferences about a population, right, from a sample. Now, the central limit theorem is what provides the theoretical foundation for confidence intervals. In my view, one of the most important result in statistical theory. So it basically, the central limit theorem, right, tells us that that a sample will fall within 2 standard deviations from the population parameter about 95% of the time, and within about 3 standard deviations of the population parameter 99% of the time. Now, the next lectures, I'm going to show you how to calculate confidence intervals for proportions, means, and how to do that in Excel. Thanks for watching.